Right, so welcome to another edition of the CLSP seminar. Before I introduce today's speaker, I'll make a quick pitch for two other seminars. There's actually going to be a follow-up talk to this talk tomorrow by Shantanu Chakravarti, and it's going to be in the afternoon in ECE. So if you're interested, if this stuff is interesting and you want to follow up, come for tomorrow's talk. And I also want to make a quick pitch for next week's CLSP seminar speaker. He's Gert from Sheffield, and he's actually going to talk, Fred just informed me, about plagiarism. And
about detecting plagiarism.
About detecting plagiarism, not how to do it better or whatever.
Actually, if you learn how to detect it, you know how to do it better.
As well. There you go. So I hope many of you will come for next week's talk as well, but in any case, I'm glad you're here today. Again, this time our speaker today needs no introduction. I'm sure each and every one of you knows him, but again, for the sake of the camera, I'll do a very quick introduction, just for posterity. We have with us Professor Gert Cauwenberghs. Of course, all of you know him as a professor in the EC department here at Hopkins. Some of you may not know that he did his PhD from, he did his bachelor's from the University of Belgium in '88. Then he went to Caltech, where he got a master's and a PhD degree in '94, and he's been with us pretty much since then. We did go away for a bit for a sabbatical to MIT, where he was in Tommy Kochil's group for a while. He does many interesting things. I'll just read off a couple of key bullets. Adaptive neural computation applied to speech and acoustic processing, focal plane processors, adaptive classifiers, low power coding and instrumentation.
I hope you won't read the whole thing.
Well, I couldn't read the whole thing. I'd probably, well, anyway. He does many interesting things, and he also has many distinctions to his name. He was the Presidential Early Career Award for Scientists Engineers awardee, and then the ONR Young Investigator. He's the Associate Editor for the IEEE Transactions and Circuits and Systems, and the new IEEE journal called Sensors. And his lab up here is called the Adaptive Microsystems Lab, which is up in Glasgow.
Thanks lots of you. Okay, so this will be a bit of both a tutorial on kernel machines as well as a talk about some of the recent work that we have been doing here. I'll be talking also about joint work with Shantanu Chakravarti. And as Sandeep mentioned, tomorrow there'll be a seminar, a grad student lunch seminar in CSP, and we'll tell some more about the details of some of the later work that I'll be talking about. So I'll start with a introduction to statistical learning theory and about BC dimension, margin generalization, support vectors, kernels, and then I'll frame this in a formulation that includes some other types of machine learning problems that we're interested in particular here for in CLSP for probability estimation and also for forward decoding sequence estimation. And I'll talk about some issues that are important: sparsity in incremental learning if you deal with very large data sets, or you care about the representation as well as the time needed for training. I'll also talk about some hardware that we developed, call them learning machines, real machines in silicon. And then so I'll talk about speech application that we have. Okay, a brief word about statistical learning theory, and I won't go in much detail here because there's a lot of math involved, and this will get us too far beyond the scope of what we want to talk about today. So just to give the intuition, and I'm sorry about the colors that didn't come out right. There's supposed to be some pink and some blue. So on the left, so you have some data here, X or vectors. We're talking about support vector machines, so you have vectors. And they have labels Y. And the task here is to classify the data from examples and then do well on unseen data. So what we care about is not just to classify the trained examples, but you want to generalize beyond the examples that were given. And so on the left is shown a valid classification boundary, which happens to be linear. On the right is a more capricious boundary. And so the point that I want to make here is that the task of classifying is in a way ill-defined because you don't know, you only know the data that they're given, and you don't know about the true function. And so smoothness is an important consideration here. So is this a better classification boundary than this this curved classification boundary? It depends on how much data you have, and depends about the purpose of the data. So statistical learning theory aims at addressing the question of what is a good classifier, or a regression machine, so more general than just classification. And so statistical learning theory links then generalization to complexity of the class of functions in which training is performed. Just to give a brief, intuitive picture is that what we know already is that the number of parameters in your system should not be larger than the number of data points. And that's a very intuitive, a very naive way of thinking about it. So there is something called a VC dimension for Webnik and Cauwenberghs that expresses some more rigorous way of expressing this trade-off between generalization and complexity, I mean the duration of generalization and complexity. And so there's some certain classes of functions that actually may have an infinite number of parameters and still generalize well by proper control of what is called structural risk, the properties of by constraining the space of the hypothesis space of functions in which you train. And just give in summary, so training the classifier with large margin, so maximizing the margin, so the margin gives a better generalization, gives less complexity, and so that leads us to support vector machines. Let me just go and explain this a bit further. So here, so we're given training data, so we're assuming here a two-class problem, and here I'll assume that the problem is linearly separable, so everything is simple. And here is then a solution which gives you the largest margin. The margin is defined as the shortest distance from the separating hyperplane, the distance to the nearest points. And so in this case, there are 3 points at which then where you reach the margin. So you can express your solution in general in terms of a parameter vector that's defines the coordinates of your hyperplane, and so W and B are defined up to scale. If you fit the scale so that on the hyperplane, on the separating hyperplane, that argument Wx plus B is 0, and on the margins, on both sides of the margin, here it's 1 and there's -1, then we can directly relate the norm of the parameter of the weight vector to the margin, to the distance, which is 1 over W. So all we have to do then really is to minimize the norm of W to maximize the margin. And so you can also then impose a constraint that in this case you want to be separate the width margin so that all the data points have to be on the correct side of the margin. So all the 1 points have to be on the right side of the where this equals 1, and then all the -1 labels have to be on the left side where this plane equals -1. Now support vectors then arise naturally from this formulation, because maximizing the margin, right, is defined in terms of those vectors where that touch the margin, and those are a select number of data points, and it turns out that a solution of W can be expressed directly in terms of those support vectors. Naturally, the solution should not depend on data points that are away from the margin, because you could move them around and still have the same margin. Right? So the solution is expressed entirely in terms of the support vectors, and it happens to be linear. We'll see later why that is. think of it easily in intuitive terms. So once we express the parameters of your weight vector as a linear combination of your data points, your vectors x, plus the labels, and some coefficients alpha. We'll talk about coefficients alpha later. You can substitute this back in the expression for a classifier, and you find this form, which is actually very powerful. It shows that, well, this is a dual formulation of the problem. So rather than expressing your solution in terms of a weight vector that defines the coordinates of your hyperplane, now the solution is expressed in terms of combinations of inner products between your input vector, x, and the support vectors, x and y. They're weighted with the labels, but also then with coefficients, which you will see later how to derive them. And so the problems are reduced to finding those coefficients alpha. Now this inner product representation is very powerful. So now there's no longer a mention of a hyperplane or of the coordinates of a hyperplane. And so here's where kernel's going to get into. So now we can express this inner product into something which will be in a kernel form, and that will allow us to do some more powerful functions, do some more powerful models. Before that, let me first just mention the more general case of classification would be one where we also want to consider outliers, and we also give them some penalty that enters the optimization. So rather than just minimizing now the norm of the weight vector, which corresponds to maximize the margin, we have now a compound measure that includes both this maximum margin, which we call structural risk, and then empirical risk or evidence, which measures then a distance from a measure of discrepancy in the data. So you assign a linear cost of a label 1 that should be on the right side of this margin. So you just measure this as a linear cost and have this with some weight c to the cost function, and now minimize that. As it turns out, this formulation still gives us support vectors, except besides the margin points, there are also error points. Error points, those are the red labels, right? The red vectors, and they also enter then the solution. So support vectors include margin vectors, the green points as well as the red points, which are in the error.
And what's the definition of the error point?
Error misclassified. Yeah.
Those are that's a zero and it's not the correct side. So
this is an interesting point. So here, for training, in the cost that we assign, we include the margin. So any point that violates the margin condition, right, is still considered misclassified as far as the training is concerned. Of course, when we now be classifying this, if we have a point here that will be perfectly valid and will be correctly classified. So this margin allows us some region over which we can tolerate some errors, and this is the key to generalization.
Can you say a word about why the margin is related to the norm of the weight vector?
I'm sorry, this I may have missed. This may have been a bit too quickly. Right. So if we scale, if we set WB, the scale of WB such that this argument is 1 and minus 1 on the margin, right? Which is mathematically formulated in this constraint, right? Then the norm of W, right, is inversely proportional to the distance, perpendicular to the hyperplane. Right? Just mathematically, there's not much to it. But as we will see later, a more intuitive or
can
more...
I ask you one more question, which maybe is obvious? How do I mean, the x's are those x's which are
support vectors.
which are the support vector, and how do I find them?
That's the interesting part, and we'll get to that
I see.
in a more rigorous formulation. All this is just intuition, of course. Right, so the solution will still depend on other points, depending, I mean, it may have been that points still enter the margin, so we'll see how we find these points and how we find the coefficients. Okay, so before then going to the actual training formulation, let's go to a more powerful representation where we can extend those linear classifiers to higher dimensions and to nonlinear surfaces and through some feature map. Let's say this is a data now, and it'll be hard to find a linear classifier. Actually, it'd be better to find a nonlinear classifier in this case. So the common trick is to apply a nonlinear map phi that transforms the data, right, the vectors in data space to feature space. And it can easily be seen that in general, applying a higher dimensional feature map, going from lower dimensions to higher dimensions, typically will make data more linear. For instance, if the feature map would consist of taking all the polynomials, all polynomial combinations, product combinations up to order, say, order 3 in all the input dimensions, then a cubic classifier here corresponds to a linear classifier in feature space. In general, you can have other feature maps, and so now what you can do is in this feature space, you find now a optimal hyperplane, a optimal separating hyperplane, one that maximizes the margin. It's really crucial to do so, because we need to control the structural risk, since now we're dealing in a very high dimensional data space. The number of dimensions could be much higher than the number of data points. And so here, you cannot just apply blind regression techniques that will horribly overfit. So you have to care here about regularization or about minimizing structural risk. And so minimizing the norm of the weight vector or equivalently maximizing the margin is the right thing to do here. Right? So this gives us the form that we just found in terms of the dual form, which has parameters alpha, which you will see, and support vectors xi and inner products. Now we can relate those inner products back to the feature, from feature space back to the input space.
You still didn't tell us what the phi is, right?
No, you
I
choose
usually
it.
said it.
Right, you can choose it.
Well, you
And
can choose it, but no doubt it's a good way and a bad way.
there are certainly bad ones, but it turns out for some applications, and there has been some experiments in image, so with the original experiments with on the MNIST dataset, that you can take different kernels and you get the same support vectors, or almost 90% of the support vectors are the same, which means that there seems to be some invariance in the trained classifier to the choice of this kernels. In practice, of course, the kernel is important, and I won't really be talking about finding an optimal kernel for data. There has been some research by Tommy Jaikla at MIT on finding, if you have a generative model, if you have a density model in your original data space, you can come up with some kernels that relate to Fisher. Fisher kernels that relate to there's an information theoretic framework to find optimal kernels. But I'll talk about some example kernels that work in practice. So for now, let's assume this is given map.
I still have one more thing. What is X here?
X, capital X.
No, in the formula.
X is the incoming example you're going to classify. The incoming, that's your...
That's the,
Yes.
the test.
That's in the features.
that's just one thing. You know, it's one of the
Yes.
Yes,
It's not bad.
it's,
Yes.
one of the vectors I don't want to
This is
work on.
notations a little bit.
Well, yeah, so the XI, those are examples, the
Yeah,
training points, actually select data points.
I thought the XI are the ones that are on the support
Those
plane.
are select, those are,
Yeah.
And
So
you
see
have
later-
class labels with those. And X is the unlabeled architecture.
So this is really Y of X, the left hand
Right.
side.
right, that's
Yes.
why this is one.
Yeah.
Y of big X.
Yeah.
So that's a prediction of X.
Yeah. That's a prediction of what the sign will be of.
Right.
Right.
We can generalize this to other things, regression, probability estimation, and we'll see that. Okay, so we can now go, we can transform this inner product back to data space through the map, and that's where kernels come up here. Because this inner product in feature space defines a vector function, actually a scalar function of two vector arguments, right, which you can define as a kernel. And then this representation gives us that formulation, right, where the inner products have been replaced now by kernels. This is a general trick. Take any algorithm. You can do PCA, for instance, right? Any algorithm that is formulated entirely in terms of inner products in some feature space or in any space. You can transform this algorithm in an equivalent algorithm using nonlinear data, right, that is expressed in terms of kernels. Just replace all the inner products with kernels, and that's just the bottom line of this technique. Of course, the whole point here is that now you don't need to compute this inner product in this high-dimensional space, which could be infinite. And the question is also, if I choose a particular kernel, any function, would any function do? The answer is no. But there is a condition under which certain k, kernel functions will be a valid kernel in terms that they can be expanded in terms of a inner product or feature. And it's very similar to how you, so a matrix can be decomposed as an outer product of vectors if it's positive definite. And so here the conditions are very similar in terms of positive definiteness, which is called immersion condition. And I won't go much into detail, that's basically what it is. Here are examples of valid kernels. And once you know the kernel is valid, then you can apply support vector machines to it. So polynomials
What is valid? What does valid?
Valid means
or
that it can be written as an inner product in the feature set.
I see.
But you're not telling us what the phi is corresponding to the state.
The phi of this, I can give you the phi of this one. Those are actually product combination. For polynomial of order 2, say, those are all product combinations up to order 2 of the input space.
All the bilinear.
Right. Same with higher order kernels. It's more difficult. For a Gaussian kernel, it turns out that you get an infinite dimensional representation. I could do it on a whiteboard, but I guess this would occupy already some of the time. Actually, those that are interested in this, I'm also covering all this material in my machine learning class, which I'm offering on Thursdays. There's also sigmoidal, a valid kernel that is more used for historical reasons because it just happens to be like a neural network. And in general, so you can think of your support vector machine now as a generalized neural network, where the input is a vector. This would be your input layer, right? Then you compute kernels between your input vector and a set of support vectors. Each of the support vector can be thought of as a hidden node in your 2-layer perceptron. So the weights connecting the input vector with each of those hidden units are not just the coordinates of your support vectors, right? And I compute this kernel on those nodes here. Then the outputs are combined with the labels and the alpha coefficients, which we'll see how to divide them. And so there's a special case of neural network where the input layer just happens to be a select set of support vectors, and where the output layer is linear, and so we need to train those coefficients. And as you see, this gives rise to convex optimization problem, which is nice. It doesn't have problems of local minima that you normally have if you do backpropagation. And also it's automatically regularized because we're minimizing this norm of the weight vector, which does some proper regularization. Okay, let me now give a general formulation of the same thing. So I have another 15-20 minutes, so that's the time. Half an hour. Right? So we're going to express a solution in terms of this, what we call a margin variable. The margin variable is a variable that is perpendicular on your hyperplane, and that measures the distance away from it. We'll express a loss function in terms of that margin variable that's constructed in terms of w times x plus b. Right? So this in Zi is essentially this, as we'll see later in a minute. And then we also have the norm of the weight vector that we care about. So x is in feature space, and of course, in a data space it corresponds to 5x. Right? So this includes support vector machines, where the first term is structural risk, the second term is empirical risk. Right? You can also think of it as some smoothness term and fidelity term in regularization networks. There's a different way of formulating. You can actually come up with the same kernels doing that framework. Or if you're a Bayesian enthusiast, you can think also of the first term as a log prior. You assume a log prior on the parameters, and then you have a log evidence in the second term. This is also nice in terms that you can get probabilities out of this model as well. And that gives rise to Gaussian processes, which are also very popular these days. The main point here is that G should be convex loss function. We have already seen one example of a loss function for the margin or the soft margin SVM classifier. We'll see some other ones. For instance, here, right, ZI, your margin variable, is expressed again as this margin variable times the label. So this should be positive for a correctly classified, for the support vector machine. It should be positive, right, and beyond the margin, which is at 1, and that's where all the points should be. So we assign little loss for points that are on the right side, and then we have some loss that rises if you're on the wrong side of your margin. In this case, the margin will be softly defined, and you can take any loss function that you like, as long as you have a convex function. You can do also the same thing for regression, except for regression, the labels are not 1 or -1, but the labels are not continuous. And then what you define is the difference between your continuous label and the prediction, which is Wx plus b. Right? And you want this to be as close as possible to 0. In this case, you still have a convex function, loss function, but it will be concentrated with a 0 loss around 0. So for this general framework, we can directly find support vectors out of this. So there's a very simple formulation, of course. Since it's convex, all we care about are the first order conditions, right? Where the ZIs are expressed in terms of this linear function. Right? So the first order conditions specify, so first of all, first order conditions in W, then first order conditions in the offset term B. Right? For W, we find directly that W is a linear combination of, if you apply the chain rule in ZI, we find directly that W is a linear combination of data vectors xi, where linear combinations relate to the derivative, to the chain rule here, of the loss function. So we can frame this in the formulation that we had initially, support vectors, where we have your labels yi, and then you have your coefficients alpha I. Directly from this we find that the coefficients, that we care about to find, coefficients are minus c, c is your regularization parameter, times the derivative of the loss function evaluated at the margin variable for that point. Right? So that's the constitutive relationship. If you satisfy this for all the training points, we're done. That's what training is. Right? And actually you don't even care whether the support vector, you don't need to look for the support vectors. Satisfying this relationship will tell you which the support vectors are. Let's see that. And the second condition then tells you that the weighted sum of those coefficients weighted by the labels also has to 0. If you don't have an offset, then the second condition doesn't apply.
Second be a very noisy thing.
There's no noise here, just mathematical formulation.
Numerically.
Yeah, we'll show. We're not evaluating G. We're actually not evaluating G. We're only doing training. If we could do this on a computer, it doesn't matter. And actually, what really matters, the thing that matters is the derivative of the loss function. I'll show you in a minute. The other observation is that, so once you have this expansion of the weight vector in terms of the support vectors, you can also write your margin variable directly in terms of, if you substitute this expression in here, you directly find the expression of your margin variables in terms of the alphas, plus Qij is your kernel matrix, which has all those dot products. Xi with xj here with this xi. Right? So those are all the dot products, including then also the labels. And this we define as a kernel matrix, right? Plus an offset term that's doing. But so we see directly that the learning problem only cares about your kernel matrix. Right? So take every pair of data points, take every pair of training points, put them in a big matrix, and that defines the training problem. We have to satisfy this relationship for where Zi is then given by this linear combination of the L-lines. Right? And then we're done finding the solution. So the only thing that matters for training is doing the kernel matrix, and looking at the property of the kernel matrix will also tell us something about the solution. One very interesting observation is about sparsity. Sparsity is important if you care about how few support vectors you need to cope. So you get sparse solutions if for many data points the derivative of the loss function is 0. Right? So if you go back to the support vector machine formulation, here's the loss function. And indeed, there could be problems with computing derivative. We'll be evaluating this, but we only care about the actual with the loss function. Well, this is the step function. Right? The loss function is this. The derivative loss function is the step function. And right away, since we know that the alphas are minus c times this derivative of the loss function, we see directly for all the data points that are on the correct side of the margin, they'll have 0 coefficients. They don't count. That's comforting. Then those points that are on the margin, they will have an alpha value between 0 and c. They're right here. And in those points that are on the wrong side of the margin, they could be still classified on the wrong side, or really be classified on that side. So all those points will have an alpha value that is c. Right? And those are called the Kuhn-Tucker conditions, or Karich-Kuhn-Tucker conditions. That tell you that either for any point, either alpha is 0, or it's on the margin, or c, or alpha is c. Right? That's basically the only conditions that you care about. And so if you will iterate a solution over the kernel matrix, then you find your support vector machine, your support vector coefficients. And, actually, that's how most techniques for solving support vector machines operate. They just satisfy the Karich-Kuhn-Tucker conditions. So as I said, you get a sparse solution as long as your data is correctly classifiable with a margin. If you have all the data points that are on the wrong side of the margin, because you have all the noise in the data, you'll be stuck with a lot of error vectors, and they all count in your expansion. So if you have 1 million data points and 10% of those are errors, then you end up with 100,000 points, and then you have a massive classifier. Even though your space, your original space, could only be 2-dimensional. So there's something wrong about that. And it gets even worse if you look at a more interesting problem for speech, where you care about regression of probabilities. So here we assume, so rather than caring about a classified label, we care about a confidence, or we want to get an actual probability, a number out of it, that expresses the posterior probability of that, or the conditional probability of that label given your data X. And one convenient form for expressing probability is a logistic function. And if you take this model and compute, well, now you like to use some log likelihood expression for cross entropy. If you use cross entropy of this in the probability model with your data, with your labels, then you find a loss function that looks very closely, that looks very similar to the soft margin SVM classifier, except it's smoothed out around the transition region. Right? And it makes sense because if you want to express probabilities, you care about this region, and there should be nothing discrete about it. So this is a natural way of formulating then a loss function to care about probabilities. Unfortunately, if you look at the derivative of this loss function, you find that nowhere it's 0. You get this function that goes between 0 and -1. So that means the coefficients alpha will be between 0 and c. But even for correctly classified points, you get a non-zero value. And so that's a bad thing if you care about sparsity. We will talk about that. Okay, now this is just technical detail, and it's important for those who want to see the connection with the usual formulation of support vector machines. So we have seen this constitutive relationship that tells you what alpha is if you know the margin variable zi, where zi itself is given in terms of the Kernal matrix. If you eliminate zi from this expression in this form, and now if you integrate this expression, you find a functional that you need to minimize in the dual parameters alpha. So this is called the dual formulation, which happens to be, so the Legendre transformation of your original formulation gives them this dual form of your optimization function, which you need to minimize. And it looks a lot like the primal. Actually, this term is identical. This expresses the norm of the weight vector, just in terms of the alphas, and then we also norm of the weight vector. And then you have potential function, g, which is then the integral of the inverse, well, the integral of the inverse of the derivative of the loss function. And so that's the potential function. That tells you something about, well, this enters an optimization problem. You can also think about the properties of the training in terms of the shape of this potential function. But really, everything is in.
What's the pros and cons in this dual formulation?
It's equivalent. So the first organizations of this is exactly the same as this is exactly the same as that. Okay? This is a formulation that is, it looks nice on paper, but when it's implemented in software, this is already implemented. Because you need to compute first order conditions in it. It looks, I mean, people that care about statistical physics like this because you see it directly as analog. But so graphically then you can interpret the same result. Right? So again, the potential function is the integral of the inverse of the loss function, of the derivative of the loss function. Right? So here again, this construction where we computed the derivative loss function for your soft margin, which is the step function here. Now we rotate our heads by 90 degrees, right? So we take the inverse, where this axis now is alpha. And now we take the integral. The integral of a constant is just a line, straight line, right? And we have walls here. So here we have a wall at 0, we have another wall at c, so those are constraints, those are hard constraints. So we find the potential function for a soft margin SVM is just a linear term in alpha, plus constraints that alpha have to be between 0 and c. If you do the same thing, so Vapnik does it with uses Lagrange multipliers and comes up with the same result. I think this is a more transparent way because now you can take any other loss function and do the same construct and find directly what happens. For instance, here we're again with logistic regression, where this logistic model of probability, where you have this loss function. The derivative is this actually tan h function, or it's also logistic. Then the inverse and the integral gives you the binary entropy function. It has infinite derivative at 0 and infinite derivative at c. That means indeed that no coefficient can be 0 or c, and that's what results implied by sparsity. Right. So we get a non-sparse solution because of this infinite derivative there and there. So I have a bright student in my lab, Shantanu, and he's looking at this and saying, well, there is another form of entropy which is also used in speech, and that's called the Gini entropy. Right? It looks like the binary entropy, but then it just has a quadratic approximation to it. Right? So why not use that one? And it's a valid. I mean, it's I guess it approximates this, except you have now finite derivatives here and there. So it means that now you can get a sparse solution. Right? take the derivative of this, you know, it's a straight line here, and then you see directly here you have nothing, which means that this translates to the inverse. You see that here the derivative of the loss function will be 0, which means so that those points won't count.
And
To get a sparse solution.
you want sparse solution because you're interested in communication in terms of kernels.
Right.
That will minimize the number of kernels.
Right. So, for instance, if you're doing timid, as we'll talk about, so if you have hundreds of thousands of data, and you know there's a lot of noise in data, or I mean, just a fact, right? So you have a lot of points in this region here, where you cannot really neglect. I mean, normally you could think of just throwing out points with very small alphas in logistic regression, but here's a formulation where you can really rigorously make them 0. Right? So this gives a sparse an expansion, kernel expansion with fewer parameters, and that's convenient. So for runtime, you have less computational complexity.
It also shows the relationship, though, between sparseness and robust, statistical robustness.
Right. So this happens to be, and also Chantal will realize that this loss function is called the Huber loss function, which is used in statistics as a robust classification. And right, so where you have a Gaussian loss function, you have a Gaussian model here, and then you have a linear, which gives you a Laplacian model. Right, so this is robust stuff. Right? So just have this actually nice from a theoretical perspective. Of course, if we care about probabilities, and from this loss function you compute the corresponding model, we find actually we're still back to logistic regression. So even though that's a loss function, we're still back to the same model as we had for logistic regression, except we have a different training formulation, which is engineered entropy. And Chantal also formulated this for multi-class. Of course, you care for speech, you care about more than just 2 classes, you care about many classes, and next Chantal about more of this. Also for regression, this is called the epsilon incentive loss function for regression. In this case, you allow a region of tolerance of plus or minus epsilon around your regression variable. Right? So if your regression y is a function of x, and your data is scattered around, right? So if this is your solution, then at any point within the tube of size epsilon both sides, right, will apply 0 loss function to the points within. So only points that are outside will count and will contribute to the loss function.
But linearly, not radically.
Linear. Right. You can also have a quadratic function, it doesn't really matter. But this is simple to be. And it turns out if you compute then the derivative of the loss function and then integrate the inverse of it, you get this formulation that looks a lot like in sparse approximation. And Girosi has shown connection to that. So where you decompose some features in an over-complete basis, it just happens to be something. There's some nice connections there that show that this does actually sparse approximation. And of course, you can see this because here we have this L1 norm that gives us a region here where so you get sparsity right here. But again, what happens for points that are outside of this region? Right? What happens to those errors? And if you have 10% or 20% errors in your data set, you're still left with 20% support vectors. Right? It turns out if you go back to the primal formulation, right, the primal formulation in terms of this weight vector W, and now substitute the expression that we had for the weight vectors in terms of your alphas. Just substitute this plane back in, and minimize that cost function, the original cost function that we had. Then you find a solution that is equivalent to the dual formulation, except there's no longer the constraint that your alpha had to be minus c times the derivative of the loss function. Right? This constraint no longer applies, which means no longer for any error your alpha needs to be c. Right? And you can understand this. So if you work out the relationship, you find that your reprimal solution and the dual solution will be equivalent as long as a difference between the coefficients lives in the null space of the kernel matrix. And it kind of makes sense. That means that the training points will be classified exactly the same way. The ZIs will be the same, right? For that set of alphas. And this opens up a possibility. So if your kernel matrix is ill-defined, and we know for sure that if you have a billion data points in two-dimensional space, the rank will be 2, right? If the feature space is two-dimensional. In general, if you have, and you exploit the null space of your kernel matrix to zero out coefficients alpha in the prime formulation. So this tells us directly that the sparsity, the number of non-zero coefficients, the degree sparsity, the number of non-zero coefficients, equals the dimension of the null space. So that gives us, right? So from the rank of the kernel matrix, directly we can find how sparse the solution can be.
And we can do that not just on paper, but we do it in practice.
So in practice, what we do is we take, this is a tedious way. So you first solve the full problem, and then you just eliminate. So you construct a null space, right? And then in that space, you just minimize alphas. Just do greedy search, minimize the L1 norm in that null space of your alpha parameters, right? Subject to this constraint, the constraint that they're in the null space. And so then this is what you find. Let's say here, of course, in general, it may be that your kernel matrix is not singular, it's full rank. For instance, we know for a Gaussian kernel that your phi, the map is infinite dimensional. That means that the kernel matrix will be full rank no matter what. Well, unless you have points that are really singular. Right? But in general, this can be full rank. But entries could be, so if you look at the eigenspectrum, it could be very diverse, right? And you can capture 99% of the variance by throwing away 90% or more of the dimensions. Right? So for instance, here's a problem using the Gaussian kernel, which is full rank, for logistic regression. And as I said, logistic regression has a problem of non-sparsity. So every point, and so labels are here 0, so x is here, and this is y. Right? So those are data points. And we want to find out the probability distribution that generates that data. Right? So you see the density is higher here, and lower there. So this would be then a valid solution to the probability. And we find so that this expansion that expresses this in terms of this Gaussian basis, right, takes all the data points. In this case, 100 data points. Right? If you do this sparse approximation in a space that has only 10 non-zero elements, then we find those 10 points, and they just happen to be interesting points in terms of the distribution. Right? And actually, the solution is exactly the same, which makes sense because in this case, eigenspectrum we allowed was 10 to the 5. Right? So we throw away all the eigenvalues or eigenvectors in the kernel matrix representation that have single value composition that are so with this spread.
But the model selection problem choosing 10
right,
is still ad hoc.
Right. So in principle, what you can do is you can plot the number that you get as a function of the spread, right? And you can find the point where it really drops off. So that will be practical.
Just find the elbow vector.
So in this case, we just did empirically. So here, if now you add the value spread of 100, then you get 6 kernel expansions, and you do worse. But is it really worse? It's hard to say.
You need to do both testing.
Because if you look actually at what it says, so in the region where you have no data, because the probability that is 0.5 rather than 0.6, which kind of makes sense. So you can argue that sparsity, intuitively, sparsity is always a good thing. So fewer ternary expansion will also help you with Occam's razor to cut off reducing complexity. Okay, I could also talk about incremental learning, but in the interest of time, let me just skip this. Basically, there's a way of incrementally learning support vector machine, one point at a time. It turns out you don't need that many, so you can do it. So using a solution with n data points, you can construct a solution with n plus 1 data points just by adding this new point as a support vector node. And it just turns out that the computation of it is not that evolved, actually it's faster than using most algorithms for perfect machines. And you can do some interesting things with that. You can actually also do unlearning, where you remove any point from the solution and then evaluate the default out there. And that's a useful metric for generalization performance. And you can do that in an amount of time that is exactly the same as it takes to train. So you can do the full default out, not estimation, full default out evaluation at the same time it takes to train. So nice problem. You can see how as a function of time, how the coefficients change as you have new data points. Some points are support vectors initially, but then they no longer, and some different relationships. So work with it with the repository at MIT. So let me give some examples now of some applications. So for vision, and so in this case, support vectors, so the task would be to classify pedestrians or looking for faces. And so support vector machines are a natural framework for this. Right, so you have it. It's important to code your data in ways where you really get features that are important for the problem, and feature representation is something that's more important than the actual classifier. So here, the team at MIT was using an overcomputed representation of wavelets, and then applying support vector machine. So taking examples and then classifying by panning a window over the field of interest, and then classifying. In principle, you can get probabilities out of this and get some model also to get rid of some spurious classifications as well. But the important point here is that number. So as a function of the number of support vectors that you have here, or how many features you have in the representation, you can get better results. Good results here is you want to have high detection with low false positives. So that's a good place here, which requires plenty of features, plenty of support vectors, and this doesn't run in real time. So they found that if you the software, if you want to run it in real time, you have to reduce the number of features, and you get some acceptable performance, but for real time, so it comes definitely at the sacrifice. So we did is, so here at Hopkins, so with Roman Genoff, who's now at the University of Toronto, is implement this in parallel view design. So where you have a wavelet dictionary and a support vector machine matrix. Well, in this case, this is just a matrix of all the support vectors, computing all the inner products, and then you compute kernels based on that. So these are inner product based kernels. So we found that this is something that we can remap into some a full parallel architecture, and actually we can combine this matrix with that matrix, get in one matrix. So we can get a structure that looks like that. We have an array of CID DRAM cells. So each element is a processor and a memory element. So you have a DRAM element together with a processor in each pixel, computing this inner product between input vector with each of the rows of this matrix, which is a support vector. And then it's quantized to the output, so you have fully digital input and outputs. And there's some nice properties of this. Of course, it doesn't make sense to do this if software is faster. You find that this has a factor 10,000 improvement in throughput per unit power. So that's the metric we care about. So for low power applications, this is a good thing. Second version has high resolution, actually get some better quantizers here, and I won't go into detail here because this is not of interest to this audience.
Right there.
Okay. Just too nasty. But here's an so an example of what comes out of this Kernal. So here we have a template which is 16 by 16, so for 256-dimensional input applied in the Kernal. And now let's convolve this over this image of Lena. I guess you all know Lena. This is what you would get if you do this on a fixed point processor with 8-bit resolution and full digital output. Just in MATLAB if you use just integers. And that's what the Kernal outputs. And it looks very similar, actually you cannot see the difference with the LC. So, and of course it's much faster than the MATLAB. So the last thing I want to cover quickly, and of course Shantanu will be telling you more about this tomorrow, is now dynamic classification. And this is really what is of interest also with this audience. So just quickly cover it, and then Chantal will give some more details. So normally what you have as state-of-the-art for speech recognition are generative models like HMMs, where you construct probabilities or densities of observed quantities as a function of states. Right? And as an alternative, you can have a discriminative way of doing sequence estimation, sequence classification, where now you construct posterior probabilities, right? It's like a posterior model rather than this maximum likelihood or Bayes type formulation, where you can directly formulate probabilities of states as a function of previous states, actually, or just history, and also the inputs, acoustic inputs. It's discriminative because it now will train this based on classification results, right? So we will train this to do well on the boundary rather than do well in the whole space. So we can, and that's good because I mean, there's generally the problem of too many parameters, and a lot of research in HMMs has gone, also here and elsewhere, has gone in reducing the complexity or smoothing results and get some better translation performance out of HMMs. I mean, really doing better density estimation. So here, so this approach also taken by Hervé Bollard and Nelson Morgan of transition-based speech recognition. Right? So the inputs modulate transitions between states, and this is what you model. So now you regress this transition probability as a function of the inputs, right? Directly. And so that really gives rise to map maximum a posteriori forward decoding. Right? So transition probabilities are generated by a large margin. That's the key here. So transition probabilities are generated by a large margin probability regression. Right? So the states qk of n this time. K is then got two different labels. In this case, for two classes, you can generalize this to more classes. You define posterior probabilities here only in the forward blade. So looking at a context that only has, so it has infinite history. So normally, if you want to compute true posterior probabilities, you also have to account for the future. We don't do this here. So we only do a forward recursion, where we compute these posterior probabilities as a function of the previous state, posterior probabilities, and transition probabilities, as we assume in market model, as we normally do. So I'll care about here is transition probabilities, and we want to regress those. That's the task here. And the advantage of this formulation is that directly you can get the decoding of states as the argmax of this of your forward recursion. So the key here is that we use a large margin classifier to regress this transition probabilities. So the right formulation would be to compute cross entropy, right, of those posterior probabilities, right, with the labels that we have. So that'll be the right thing to do. Plus we also add this margin term here, right, minimizing the norm of the weight vector. Right. And the parameters again are the transition probabilities, right, going from one state to the other, which enter directly with alphas. If you directly would minimize or maximize this function, this cost function, this formulation, this will be non-convex and cumbersome because the alphas depend on the entire history. And so if you change the parameters, it will change everything, and that's messy. We actually tried this initially, and this was not getting us anywhere.
Is the idea that each frame is labeled?
You don't have to actually. So in Timid it is labeled, but as we see, the formulation here is similar to EM, that we can have missing labels because we're filling in labels. So the key here is that we formulate an upper bound by, so you have this forward recursion from the previous alpha I minus 1 to the new alpha I, which involves those transition probabilities. Let's take, so that's what you have in this log here. Let's just take that. So you have here the sum of all transition probabilities times the previous alphas. Right? We can take this out of the log, and we can do that in inequality. Right? So if you do that, if you take that the summation out of the log, what we find now is find, actually we don't take the alpha. So if we take the alphas out, the previous alphas out, then we still need the pi's here, and get this expression here. And so get the log of the transition probabilities times, and then what you have here are the previous posterior probabilities, right, which now enter as weights in regression. So now we have formulation which is exactly the same as we had for density, for condition probability estimation, right, which we had for instance, logistic regression, the same formulation. So this is condition probability that one estimate, and this is now again a convex problem if you use for this expression, for instance, your logistic function. So we're back to the logistic regression or GDSDM, which we know has a better formulation.
Is that like making independent decisions?
So the thing is, what we do, we think of it as follows now. So there's also a naive way of doing it. You would take every transition between the previous state and the next state, take the labels, and just train the SVM that connects the previous label next to it. That will be bad, because that will not be the right thing. This is a better formulation, but actually what this does is something between. Right? So what this does, it replaces the outgoing labels, the previous state labels, with their posterior probabilities. Right? And then still uses the labels of the state where it ends up in for the training. If you don't have, I mean, so you replace it with the actual alphas. So if you don't have labels, you just don't train those. And so this is good for missing labels or noisy labels, because it fills in data. So what we have applied here is just doing recursive map training. We start by just training using the labels, because we have nothing else. We don't have alphas to start. So you take the previous labels and new labels to train SVMs that take those data points. And so for each outgoing state, you have one SVM. Right? For each outgoing state, you have one SVM that regresses the probability of being in one of two states in this case. Right? And so we just train an SVM based on that. I mean, a logistic regression based on that. Then we go one step back, right? And now, so we apply the classifier to find now the alphas for, so we go 2 steps back, compute then the result from our classifier that we had from the previous iteration. This gives us now alphas, additional, and use those as the weights, the labels of obtaining those classifiers. And if we keep doing this, eventually this converges. Actually, we have a conversion proof for the EM version of that, but we don't have a version for this, but actually it works always. And so then you can go back at a deeper depth. And the depth at which you go will determine also how the context you care about. You can't keep going infinitely, because at some point it's going to diverge. But so you can define this depth based on the characteristics of the data. For instance, for vowel recognition, for phoneme recognition, you look at what's a typical length of a phoneme. And so then apply this then to phoneme recognition on the timid data. This shows a small excerpt of the data where you can see, as you can really see here, there's a Kernal matrix. Again, the Kernal matrix has all the data, has all the information about the data. And you see for different classes, here this is just classifying vowels, stops, fricatives, etc. Right? So for different classes, you have the different. So the Kernal matrix should have high values on the diagonal, right? If you want to reclassify well. Support recognition takes this and then does a reasonable job. Now FDKM, which does the label substitution with the alphas, does better. So incorporating this context through recursive training does need better than just applying static classifier, which just makes the decision between labels. And I think I'll stop there. Again, so I should make a plug to Chantana's talk more, which would be a little more this time. And I'm late, so I guess I'm not sure how many questions we'll take.
We're still reading the
The conclusions. I think I said that. We have convergence proof for the EM version. There's no convergence proof for this.
Yes.
But actually, we have a version which we haven't really tried, which would be rather than taking different depths of decoding and iterating in the depth, incrementing the depth, is to mix the label that we have with the alpha of the previous step. And if we mix this with different, convexity, yes. So if we change the parameter of, if we start, of course, we only have labels, so we sort the labels and then we can decrease that T-net parameter, so we increase in the weight of the actual alpha. So if you play with that, I think this you can probably prove that this is a convex thing, so you can probably prove something
Thanks for that.
Thanks.
Skipped over the circle.
Yes, for you.
Okay, well, done. Any more questions, comments?
Any questions, go ahead.
Keep all the questions for tomorrow.